Prepare for revolution seems a bit overly dramatic for the opening of a YouTube video. Thankfully, I'm a dramatic person. Prepare for revolution. Actually, prepare for several different revolutions, all happening at once. No, it's not the end of the world. This is an altogether different kind of revolution. Technology is rapidly evolving, and this is especially true in fields like biotech, neurotech, and applications related to AI. It is my contention that, within the next few decades, the confluence of all this progress, happening in such disparate fields at once, combined with the law of accelerating returns. The tendency for technological progress to accelerate the more advanced our current technology becomes, will lead to cures for virtually every type of disability. These cures will take one of two forms: literal and functional. The end result of this will be what I call the post-disability world. A world where disability is no longer part of the human experience, either because it has been outright eliminated by regenerative medicine or rendered irrelevant by advanced assistive devices and other compensating technologies. This is a bold claim, I know. I am well aware of how grandiose, maybe even a little bit utopian, it sounds. However, the overall goal of this channel is to back up this claim. To that end, in this video we're going to take a look at the different types of cure on a conceptual level, as well as several of the relevant technologies that I believe will lead to these cures. But first, you might have noticed that I sound a bit stilted. This is because the voice that you have been listening to is not my real voice, but the output of a sophisticated text-to-speech AI platform. I have cerebral palsy, which is the primary source of my interest in this topic. As part of my disability, I have a severe speech impediment. If I had narrated this myself, hardly anyone would be able to understand it. Thankfully, I have MRF. MRF allows me to type anything that I want to say, and have it converted into a synthetic voiceover within seconds. It's actually a great example of what I would call a partial functional cure. If you think that you might want to try MRF for your own video projects, follow the link in the description. As the Reneural project's first full-length production, what follows is meant to be a high-level overview of what the channel is going to be about and what kinds of topics we're going to be covering. As such, it is a real tour de force of the exciting advancements being made in a broad swath of different fields, including gene therapy, stem cell therapy, bioprinting and tissue engineering, brain-computer interfaces, humanoid robots, and autonomous vehicles, as well as some discussion of how those fields may intersect to create hybrid technologies that could potentially offer an even more comprehensive restoration of normal functioning. Part 1. 2 Avenues to a Post-Disability World. I thought I'd begin by explaining exactly what I mean by literal cures and functional cures, although you've probably already guessed at the basic idea. A literal cure for a disability is pretty much what the name implies: some drug or procedure that repairs or reverses the underlying medical condition that is causing the person to be disabled. A functional cure, on the other hand, is a bit more complicated as a concept. Broadly speaking, it can be defined as any piece of technology which compensates for the disability without modifying the underlying medical condition. In other words, the medical condition is still present, but its impact is lessened. Unlike literal cures, functional cures can either be partial or complete. As such, assistive devices, such as wheelchairs and hearing aids, are partial functional cures. More advanced assistive devices, such as some of the ones that we will discuss later, edge more towards a complete cure. Ideally, future functional cures will compensate for the underlying medical conditions to such an extent that they will be made irrelevant for the purposes of daily functioning. In such a case, they would become equivalent to literal cures on a pragmatic level, while still creating a slightly different experience.
Hey, Patch, how's the arm?
Looking good. Still got a few nerves, though. Shed's been telling me how the prosthetic's gonna hook up. I've been signed on long enough to get one with force feedback, pressure and temp sensors, the whole package.
I know. What you should have is that new biogel they developed on the inner planets. Then you wouldn't need a prosthetic. It regrows the limb perfectly.
I'd rather a belt-to-build fake any day.
Because you're stubborn as hell.
For an easier way to visualize this idea. Pun intended, as you will see. Let's turn to another piece of science fiction. In Star Trek: The Next Generation, the blind character Geordi LaForge is portrayed as wearing a visor that gives him the ability to see. Although never explicitly called a brain-computer interface, that's exactly what it is. It converts light into electrical impulses, which are then fed directly into his visual cortex. As such, it represents a functional cure. In the 1998 film Star Trek Insurrection, we see Geordi's optic nerve regenerated, an example of a literal cure. We live in an era in which the science fiction of my childhood is fast approaching reality. The Elon Musk-founded company, Neuralink, is currently working on a device that is basically Geordi's visor. Here's a clip of Musk and his team explaining their ambitions.
For the first two applications we're going to aim for in humans are restoring vision, and I think this is like notable in that even if someone has never had vision ever, like they were born blind, we believe we can still restore vision. Because the visual part of the cortex is still there. Yeah, even if they've never seen before, we're confident that they could see.
This is a schematic of what a visual prosthesis using our N1 device might look like. A camera, the output from a camera would be processed by an iPhone, for example, which would then stream the data to the device, and the image would be converted into a pattern of stimulation of the electrodes into visual cortex. With 1,000 electrodes, we might be able to produce an image resembling something that you see there on the right. But as Avinash told you, our next generation of the device will have 16,000 electrodes. If you put a device on both sides of your visual cortex, that would give you 32,000 points of light to make an image in someone who's blind. Our goal will be to turn the lights on for someone who's spent decades living in the dark.
At the same time that this is happening, breakthroughs in other fields are also showing promise for literally curing certain types of blindness. Less than a year ago, at the time of writing, a joint effort by 3 universities from around the world, Duke NUS Medical School, the Singapore Eye Research Institute, and the Swedish Karolinska Institute, ran a preclinical trial using stem cells to partially reverse blindness in mouse models of macular degeneration and retinitis pigmentosa, a genetic eye disease that causes the breakdown of photoreceptors. The study, led by Dr. Tae-Wee Goon, assistant professor of the Center for Vision Research at Duke, involved culturing human embryonic stem cells with certain proteins that are involved in normal eye development. These proteins cause the stem cells to differentiate into photoreceptor progenitors. When the progenitors are then transplanted into the eyes of mice that have had their immune systems damped down to avoid cross-species rejection, they differentiate further and integrate into the native tissue, partially restoring sight. Around the same time, in Quebec, a gene therapy treatment for a particularly devastating form of retinitis pigmentosa, called Leber's congenital amaurosis, or LCA, was giving an 11-year-old boy his sight back. The new drug, called Luxturna, was developed in the United States and subsequently approved by Canada's Food and Drug Administration. The treatment uses a man-made virus to deliver CRISPR proteins to photoreceptor cells in the retina, which then correct the mutation causing the degeneration. Without treatment, those born with LCA gradually lose their sight, often going completely blind by the time they're 40. That was the prognosis for William Kairala, a resident of Quebec, who became the first person in the country to receive the treatment. Before, William had trouble seeing during the day, and was practically blind at night. Now, after receiving the gene therapy, he has been able to play night soccer with his dad. The family is currently planning to go camping so that William can see the stars for the first time. Dr. Flavio Rezende, an ophthalmologist and one of the surgeons who performed the procedure, had this to say. To convert an untreatable disease into a treatable disease, for a physician, in their lifetime, in their career, it's very rare. It's a very special opportunity we have to impact medicine into the future, and the future is the present. It's very rewarding. This confluence of multiple avenues for addressing a given disability, all coming online at more or less the same time, is what I refer to as the biomedical revolution, and it is why I am so optimistic about the prospect of ending disability. Going forward, I believe that this will play out again and again. The best way to imagine what this will be like in the future, other than science fiction, is to look at what has already happened. For my entire life, my father has worn glasses to correct for nearsightedness. Had he been born hundreds of years ago, before the invention of the convex lens, his condition would have been a disability. But, because it can now be so easily and readily compensated for, we no longer even conceptualize it that way. Indeed, even though we now have LASIK, which is closer to a literal cure for nearsightedness, and similar conditions, many people still opt for glasses or contact lenses, because they do just as good, or nearly as good, a job, but are less expensive. And also presumably because they still feel trepidation about intentionally shooting lasers into their eyeballs. As technology advances further, disabled people may find themselves with an embarrassment of riches when it comes to ways to overcome their condition with personalized solutions that match their specific needs and preferences. Between literal cures and functional cures, the very concept of disability may become obsolete by the end of this century. Part 2. Literal cures. To literally cure a disability is to fix the problem at its root, essentially. As such, the two main methods for literally curing disabling conditions are going to be gene therapy and stem cell therapy. Gene therapy, also known as gene editing, involves changing the DNA of cells, and therefore how those cells behave and function. The original gene editing tool, the CRISPR-Cas9 system, was developed by Emmanuel Charpentier of the Max Planck Institute for Infection Biology in Berlin and Jennifer Doudna of the University of California, Berkeley, for which they shared the Nobel Prize for Chemistry in 2020. I made a video on the various ways in which the CRISPR-Cas9 system has been modified and expanded upon, which you can check out here. Besides the altering of DNA, progress is also being made in our ability to deliver CRISPR therapeutics to where they are needed. Until recently, the safe implementation of gene editing within the body, or in vivo, has been a major obstacle to bringing such treatments to the clinic. To this end, the lab of Jennifer Doudna at UC Berkeley has recently taken an important step: the development of a method of selectively editing cells based on cell type. Traditional CRISPR delivery systems are prone to editing bystander cells, which can decrease the efficacy of the gene therapy by wasting the genetic editors on healthy cells. In addition, every cell that is edited increases the risk of off-target edits, where the CRISPR enzymes alter the wrong part of the genome, potentially leading to cancer. To reduce bystander editing, the Berkeley team combined CRISPR with another biotechnology: monoclonal antibodies. These are artificial proteins which correspond to receptors, or antigens, on the surface of cells. Since each cell type has unique antigens, membranes coated with monoclonal antibodies can be engineered to seek out specific cell types. In the past, such membranes have been used to do things like deliver toxins to cancer cells in vivo. Here, they were used to deliver CRISPR proteins to the T cells of mice, with humanized immune systems, transforming them into CAR T cells without affecting other cell types. If gene editing allows us to change the behavior of malfunctioning cells, stem cell therapy allows us to replace cells lost to injury or disease. Stem cells are cells which exist in an undifferentiated state and consequently can both multiply and transform into other types of cells. Although there are many types of stem cells, the most dramatic work in regenerative medicine revolves around induced pluripotent stem cells, or ISPCs. These are embryonic-like stem cells, which are made by reprogramming adult cells, thus allowing us to circumvent the ethical issues associated with the use of fetal tissue. As a bonus, since they can be produced from the patient's own cells, the risk of rejection is eliminated. The technique for deriving iPSCs was pioneered by the Japanese researcher Shinya Yamanaka, for which he received the Nobel Prize in 2012. I made a video about this, which you can check out here. Much more recently, the Yamanaka method has been iterated upon. Back in August, researchers at the University of Western Australia and at Monash University Melbourne introduced a new method for producing induced pluripotent stem cells that is more effective at reprogramming cells. This new method, called transient naive treatment or TNT, adds an extra step to Yamanaka's that causes the medium that iPSCs are cultured in to better mimic the natural environment of early embryonic development. TNT-produced induced pluripotent stem cells more closely resemble embryonic stem cells, both in their epigenetic profiles and their behavior. This could lead to safer stem cell therapies that are even more effective at integrating into the body. Closely related to stem cell therapy is bioprinting and tissue engineering. Bioprinting utilizes 3D printing to construct artificial tissues, which can then be transplanted into the body. The 3D printers are loaded with bioinks, which consist of stem cells suspended in a solution of biomaterials. These biomaterials retain their shape after printing, thus providing a scaffold for the stem cells to grow into, as well as nutrients, transcription factors, and chemical agents that support the cells and encourage them to multiply and differentiate as needed. Several bioinks may be used, consisting of different cell type and biomaterial mixes. Guided by a digital file, the printer deposits the bioinks, layer by layer, in a specified pattern, thus creating complex structures that mimic as closely as possible native tissues. Most excitingly for people like myself, who live with cerebral palsy and other forms of brain damage, 2 recent breakthroughs have been made in 3D printing neural tissue. The first is a study put out in October by the Oxford Martin Program on 3D Printing for Brain Repair at Oxford University, which pioneered a new 3D printing technique that uses human iPSC-filled droplets to precisely position cells. They used 2 different bioinks, made with different types of neural progenitors, corresponding to different layers of the cerebral cortex, to create synthetic brain tissue. When grafted onto brain slices taken from mice, the tissue integrated both structurally and functionally with its organic counterpart. Going forward, the team hopes to further develop their approach to create more complex, multi-layered constructs that even more closely recreate the architecture of the cerebral cortex. This is significant since this part of the brain is heavily involved in movement, communication, and cognition, and is often severely affected by brain injury and stroke. A second study, put out earlier this month by the University of Wisconsin-Madison, produced a different kind of breakthrough. Whereas the Oxford study focused on structurally recreating human neural tissue. That is, ensuring that the different cell types were in the correct position relative to each other so as to replicate the brain's layered architecture. This study's primary concern was functional duplication. The researchers wanted the neurons to connect and communicate in a more natural way. In the past, attempting to bioprint brain tissue to both structurally and functionally recapitulate the genuine article involved a catch-22. For the printed tissue to hold its shape, the biomaterials had to be stiff enough that the construct wouldn't collapse under its own weight. However, this stiffness would impede axonal growth, making it difficult for the fledgling neurons to connect. Also, since we haven't yet mastered the vascularization of printed tissue, the cells on the insides of 3-dimensional constructs, such as the Oxford team's, often died from oxygen deprivation, further hampering network formation. To get around this, the Wisconsin-Madison team printed their cell layers horizontally rather than vertically, meaning that, if their neural tissue was to be transplanted into a human brain, it would first have to be rotated 90 degrees so that the cortical layers would line up. This solved both problems at once. The construct could be thin enough that softer biomaterials could be used without it collapsing, thus allowing the neurons to branch out and form synapses, while also making it possible for oxygen to reach all of them. The result was what has been described as the first functional, 3D printed human brain tissue, which is to say that the neurons made appropriate connections both within and between cortical layers. The team further confirmed that the cells were communicating with each other, both electrically and neurochemically. When astrocytes and glial cells were added to the constructs, the neurons spontaneously formed relationships with them that matched those seen in real brains. The Wisconsin-Madison team has not specifically indicated their approach as a way of repairing brain damage, presumably because the necessary thinness of the constructs would make it difficult to do so cost-effectively. However, perhaps the two methods could be somehow combined to get the benefits of both. Part 3. Functional cures. Even as stem cell therapy, genetic editing, and other regenerative medicine approaches are beginning to pick up steam, other technologies are also being developed that may allow us to mostly, or even completely, compensate for many disabilities. Let me start by acknowledging that, yes, all of the technologies discussed here are being worked on by companies headed by Elon Musk. I make no bones about the fact that I am an Elon fan, though I will also cover his main rivals. The first of these is the brain-computer interface. We have already discussed Neuralink in the context of developing a visual prosthesis for the blind. The company's more immediate goals, however, are a bit humbler. Their first device aims to give people with severe mobility issues the ability to control computers with their minds. Elon announced on Twitter just a few weeks ago that the first human patient had been implanted and was recovering nicely. Synchron, which has similar ambitions as Neuralink and is currently ahead of their competitor, just made a deal with the German manufacturer, Aquandas. This will give them exclusive access to Aquandas's unique technology, which they need in order to make a vital component of their device as they gear up for commercialization. So far, Synchron has implanted 10 patients, 6 in the US and 4 in Australia, as part of their ongoing clinical trial. Meanwhile, Precision Neuroscience, another BCI company, just teamed up with the Lawrence Livermore National Laboratory, or LLNL, with the aim of developing a mass-produced neural implant. The LLNL has an extensive background in manufacturing thin-film microelectrode arrays, as well as a dedicated microfabrication facility, which it will leverage to help Precision develop the next generation of its minimally invasive device. They hope to get FDA approval sometime this year. 3 other BCI companies worth keeping an eye on are BlackRock Neurotech, Palindromics, and Onward Medical. Another rapidly advancing area of tech that will likely have the effect of lessening the impact of disability on people's lives is that of humanoid robots. The appeal of humanoid robots is that they are general purpose, meaning that one robot can be made to do many different tasks. With advanced enough AI, they could even be asked to do things they have never done before. This is perfect for dynamic situations in which what needs doing changes from day to day, such as helping disabled and elderly people live independently. The humanoid robot that most viewers will be familiar with is Optimus, which is being developed by another Elon Musk-owned company, Tesla. Tesla released this short video back in December showcasing their latest version of Optimus. So far, Elon and the Tesla team have only talked about using their robots in factories as a supplement to the human labor force. However, they are only one of several companies working on humanoid robots. Another of these companies is Figure AI, Tesla's main rival in this space. A few weeks after Tesla put out their video, Figure released one of their own, showing their robot, Figure 1, making coffee. This is a bigger deal than it might seem, as the robot is shown making a mistake and then correcting itself without human intervention, indicating that it has reached a level of autonomy such that it can now do useful work. Here's the clip.
Hey, Figure 1, can you make me a cup of coffee? Thanks.
Brett Adcock, the founder and CEO of Figure AI, has said that, in the short term, they plan to use Figure 1 to mitigate labor shortages, much like Tesla. Long term, however, as the technology matures and costs are driven down through scaling, he is excited about branching out to other use cases, including specifically in-home assistance and elder care. They seem to be well underway, as it was announced only a week after the video that BMW had made a deal with Figure and was now experimenting with having the robot do a limited number of tasks for them at one of their plants in Spartansburg, South Carolina. Some other noteworthy companies working on humanoid robots are Apptronic, 1X Technologies, Agility Robotics, Fourier Intelligence, Unitree, Sanctuary AI, and Xiaomi. Finally, the last emerging technology that I want to mention is autonomous vehicles. Unlike the others, this one may come as a surprise. However, transportation is a major challenge for the disabled. Many disabled people are unable to drive, whether because of vision loss, coordination issues, or some other impairment. This has a real impact on autonomy and personal freedom. Self-driving cars have the potential to solve this problem, whether they are personally owned or part of a robotaxi service. The advent of ubiquitous, safe, and reliable self-driving cars could therefore be a game-changer for such people. Of course, the leader in autonomous vehicles is, again, Tesla. Tesla began a slow rollout of version 12 of its full self-driving beta program in November and began releasing version 12.2 to limited customer vehicles a few weeks ago. This version is different from previous ones in that it contains no written computer code whatsoever, but relies entirely on what is called end-to-end neural networks trained on millions of videos in Tesla's Dojo supercomputer. In layman's terms, this version is entirely AI-driven. Hence the protracted rollout, as this is essentially experimental technology. Tesla fans are hopeful that a non-beta version may be released by the end of this year. Besides Tesla, some other companies that are making headway in the field of autonomous vehicles are Waymo, Cruise, Mobileye, Baidu, and Zeus. Part 4. Literal cures and functional cures compared. Although what I have called literal cures and functional cures can generally be seen as two different ways of accomplishing the same thing, they are obviously not completely interchangeable. As I see it, each has two major advantages over the other. The first major advantage of literal cures is that they are permanent. The functional cures that I mentioned, in contrast, tend to be the sort of thing that would require regular maintenance of one sort or another. To illustrate this point, imagine that I had a microchip installed into my brain that took over some of my neural functions and, for all intents and purposes, cured my cerebral palsy. That would be great. But that chip would most likely have to be replaced every decade or so. At the very least, it would have to be charged regularly. If I ever found myself in a situation where I lost access to the infrastructure that maintains that chip for an extended period of time, such as during a natural disaster, after a while I would go right back to being disabled. Compare that to a situation where I receive a 3D printed neural graft, some future iteration of what the Oxford or Wisconsin-Madison team produced, and the difference becomes clear. Those neurons, produced from my own stem cells, would be mine, meaning that nothing could take them away from me. The other advantage of literal cures is that they have the potential to become comprehensive one-and-done solutions. That is, once things like genetic editing, stem cell therapy, and tissue engineering are perfected, they could be used to completely reverse many disabilities. Obviously, we have a ways to go before the technology reaches the level of sophistication necessary to make this a reality. My point is that all of the hurdles before us are technical challenges. There is nothing, in principle, stopping us from doing this. In contrast, functional cures, as mentioned earlier, are often only partial, which is to say that they would likely be applicable in some areas of the disabled person's life, but not in others. The example that I gave of a single brain chip completely curing cerebral palsy is, in reality, very unlikely. The same could be said of the other methods of functional cure. Even humanoid robots would have their limits. At least until the AI gets really good. Thus, in order to become functionally non-disabled with such approaches, many disabled people would likely have to take a piecemeal approach, using different technologies to compensate for different aspects of their disability. Literal cures, because they get down to the root of the issue, would most likely offer an altogether neater solution. Functional cures, on the other hand, have the advantage of being reversible. The flip side of being permanent. If you decide that a personal robot or self-driving car isn't for you, then you can return it or sell it. Even in the case of brain-computer interfaces, technological advancement will make them safer and easier to remove as time goes on. This is important for two reasons. Firstly, no technology, no matter how well designed and tested, is going to be completely without mishaps. Things like adverse reactions, unintended consequences, and just plain old changes of heart are more or less inevitable, even while we take steps to minimize them as much as possible. Functional cures, in other words, will require less of a commitment. Secondly, because functional cures are generally safer, they could end up hitting the market first, in many cases. Much of the reasons why clinical trials take so long and are so expensive is exactly because we are trying to minimize such risks. This makes sense when it comes to any medical procedure, but it is especially true when it comes to things like stem cell therapy and gene therapy, which fundamentally alter the body, in a sense. In contrast, while autonomous vehicles will be subject to their own regulatory and safety testing, and humanoid robots, especially those that will be operating in homes and caring for the elderly, will undoubtedly need some kind of oversight and safety testing as well, it most likely won't be quite as rigorous as that of the more directly medical solutions. The second advantage of functional cures is that most of them will be available to non-disabled people as well as to the disabled. This might seem like a counterintuitive point. Why would the fact that non-disabled people will also have access to self-driving cars, humanoid robots, and, arguably, brain-computer interfaces be to the advantage of disabled people? The answer is essentially because of the effect of supply and demand. Because the non-disabled represent a far larger market, there will be an incentive for more companies to develop and provide the technology. Competition tends to drive down costs and spur innovation, which, I believe, will ultimately benefit disabled people by making functional cures both affordable and more effective. I would further argue that, in a sense, this has already happened. Indeed, it is happening all the time. All else being equal, I am much less disabled than I would have been had I been born 100 years ago. For sure, this is partially because the world has become more accommodating to disabled people, thanks to the efforts of disability activists and the passing of the Americans with Disabilities Act. However, it is also, in large part, due to the simple fact that technology has progressed so much in the intervening period. Something as simple as DoorDash can at least partially make up for the inability to drive, and having a speech impediment isn't as much of a disadvantage in a world of text messaging, email, and online chat services. The amazing thing is that most of these advancements were made not to help disabled people, but simply to make the lives of non-disabled people more convenient, which I really view as a win-win. Case in point. When I was a kid, my parents tried to get me a device called a Delta Talker to help compensate for my speech impediment. It was essentially a keyboard that you carried strapped to your shoulder that had a number of pre-recorded words and phrases. I ended up not getting one because my parents were quite poor at the time and their insurance refused to pay for it, stating that it wasn't necessary for my survival. Flash forward 30 years and anyone with a tablet or iPhone, which almost everyone has these days, can download any number of apps that convert text to speech essentially for free. Many of the technologies that we discussed in the context of functional cures, when subjected to the free market, can be expected to follow this trajectory. Elon Musk famously has a plan for Tesla to work its way down from an expensive, low-volume car to a cheap, high-volume car, and he has more recently talked about manufacturing a $5,000 electric vehicle that would be completely autonomous. In the meantime, we can expect autonomous robotaxis to become common once the technology gets up to snuff. Likewise, elective brain-computer interfaces, even the invasive kind, are more plausible than one might think thanks to surgical robots and ultra-thin threads. The stated long-term goal of Neuralink is to merge our brains with AI, after all. And honestly, who wouldn't want a robot butler? In sum, functional cures will probably be available first and will tend to be safer and cheaper, but only offer partial and impermanent solutions, whereas literal cures offer a more complete and permanent solution, but will carry more risk, be more expensive, and take longer to develop. This will remain true, at least in the beginning. Long-term, literal cures may catch up in terms of safety and cost-effectiveness. Part 5. Hybrid Cures. So far, in this video, I have, for the sake of simplicity, treated functional and literal cures as discrete categories. But, of course, reality rarely is as neat as we would like it to be. Therefore, in this section, we're going to cover two more approaches to curing disabilities. Biohybrid interfaces, which combine aspects of both approaches, and epigenetic editing, which arguably straddles the fence between the two. Biohybrid interfaces are a subtype of brain-computer interface that incorporates stem cells and tissue engineering into their design. Traditional BCIs have always struggled with foreign body reactions, wherein the immune system tries to cover the electrode with scar tissue in order to quarantine it from the rest of the body. This scar tissue can impede signals from moving between the device and the neurons, and that, combined with the degradation of the probe itself, leads to a gradual loss of signal and, with it, the usefulness of the BCI. Stem cell therapy, when applied to nervous system regeneration, has likewise hit a number of speed bumps on its way to the clinic. The fledgling cells often struggle to connect with the native ones at the injury site due to the damage without some sort of hydrogel scaffold to guide them. In biohybrid interfaces, the two methods are combined in such a way that they compensate for one another's shortcomings. A layer of iPSC-derived cells is added between the electrode and the biological tissue. These cells act as an invisibility cloak, preventing the immune system from even knowing that the electrode is there. Meanwhile, the electrode, coated with hydrogel, provides the guidance that the new cells need to grow into the native tissue. Instead of the electrode interacting directly with native neurons, the stem cell-derived ones act as intermediaries. Recently, University of Cambridge researchers demonstrated a working biohybrid interface in a rat model. Human iPSCs were cultured into muscle cells on a thin, flexible microelectrode array using a specialized hydrogel scaffold. The array was then affixed to the end of a severed nerve bundle in the rat's forearm. This specific type of muscle cell was chosen because they naturally grow to connect with nerve endings, and the rat was immunosuppressed so that its body would accept the human cells. Within 4 weeks, the implant was able to record electrical signals from the nerve. Not only did the signal not degrade over time, but it was actually shown to have higher resolution than that seen with traditional BCIs. What's more, the human cells survived for the duration of the study, which was 28 days, thus demonstrating long-term survivability. In the near future, the Cambridge researchers believe that they will be able to use this technology to both restore function to paralyzed limbs as well as provide amputees with intuitive, thought-controlled prosthetic ones. Longer term, by varying both the material used to create the microelectrode array and the cell types derived from the iPSCs, they hope to be able to interface with different parts of the nervous system to treat a wider range of conditions. On that note, the lead author of the paper, Dr. Amy Rockford, recently did an interview with one of the hosts of the BCI Guys YouTube channel. She had this to say about what she's working on now.
We've got a novel optogenetic visual prosthesis, and we call this the Flex LED. And based on a combination of, thin film retinal display and optogenetic activation of these retinal ganglion cells, we're targeting diseases like retinitis pigmentosa, macular degeneration. So the idea that we have is that since the retinal ganglion cells, the output of the retina, we could stimulate them directly and restore visual input to the brain, even without replacing the photoreceptors. So essentially, it's kind of like a combination approach. So we're working on an optogenetic gene therapy, as well as a high-resolution film display. So we use this in a rabbit model of photoreceptor degeneration. So we had optical stimulation of the retina using this Flex LED that elicits activity in the visual cortex, which is pretty cool. And this technology is kind of readily scalable to hundreds and thousands of pixels. So providing like a route towards implantable optogenetic visual capabilities of generating vision by stimulating these RGCs at like a near cellular resolution.
We discussed retinitis pigmentosa and macular degeneration in Part 1. Optogenetics is an alternative approach to treating such degenerative eye diseases by using gene therapy in tandem with optical technology. The Flex LED, from what I can tell, adds tissue engineering to this, thus combining stem cells, gene therapy, and BCI tech. One can easily imagine gene editing approaches like Luxturna being further added to both prevent the further death of retinal cells and functionally replace those already lost. Of course, the optimal combination would depend on the patient. My point, following the one that I made in Part 1, is that, with all these options coming online at once, not only is there an increased chance of any one of them being able to completely reverse a given disability, but there are also more opportunities for synergies to emerge, where a combination of approaches offers a more complete restoration than any one could, alone. In contrast, other approaches may allow for more varied trade-offs. Epigenetic editing is essentially a way of achieving a similar effect as gene editing without modifying the DNA itself, either by editing messenger RNA, the step between the gene and the protein which expresses that gene, or by inducing alterations in the cellular machinery which controls which genes are expressed and at what levels. Unlike in gene editing, the changes to genetic expression that are induced via epigenetic editing are transient. This is because the cell is constantly producing new messenger RNA to be transcribed, and the cellular machinery controlling gene expression is constantly in flux. This technically makes epigenetic editing a functional cure despite its resemblance to and close relationship with gene editing. As mentioned in Part 4, functional cures have the advantage of being reversible, which comes in handy anytime that there are adverse consequences associated with a medical intervention. Epigenetic editing shares this feature. Because its effects wear off after a certain period following treatment, it provides a safer alternative to gene editing. In exchange, it has to be periodically renewed, and thus makes the patient dependent on a kind of maintenance infrastructure like other functional cures. On the other hand, epigenetic editing shares in common with literal cures the feature of being comprehensive. More so, in fact, than gene editing. Very few disease states, and therefore disabilities, are caused by a single gene. More often, several genes are involved. While it is possible to alter multiple genes with gene editing, each edit introduces the possibility of off-target edits and/or mutations. Epigenetic editing, because it avoids altering the DNA itself, doesn't suffer from this drawback. As a consequence, it can be used to tinker with entire gene networks, potentially leading to a more complete restoration of normal function. What's more, whereas gene editing can alter, add, or delete discrete genes, epigenetic editing gives the option of altering some, but not all, of the messenger RNA associated with a gene. This allows it to act more like a dimmer switch than a simple on-off switch in regards to the expression of that gene, thereby offering more nuanced control. Going forward, we may find even more solutions that combine aspects of literal and functional cures, adding yet more options. Conclusion. I hope you've enjoyed this overview of the parallel trends, which could, taken together, end up spelling the end of disability in the coming decades. Future videos will be more focused, presenting deep dives into topics like the ones covered in passing here. As I close out this video, I feel I should briefly address not one, but two elephants in the room. Elephant number one is the fact that I have here unabashedly spoken of disability as primarily a medical phenomenon, something to be treated and, eventually, eliminated. I am well aware that, in some circles, this idea has been rendered taboo. Many of my fellow disabled people and their allies will be offended that I conceptualize disability this way. They believe that disability is an identity to be celebrated and cherished, and that to suggest otherwise, to speak openly of curing any disability, is to devalue those who have the disability. First of all, I would just like to point out the obvious fact that I am living proof that not all disabled people feel this way. And while one might suppose that I and others, like me, are just exhibiting internalized ableism, I trust that more reasonable viewers will recognize this as an ad hominem. Secondly, while there isn't enough time left to go into detail as to why, I just don't think the arguments for treating disability as an aspect of personal identity actually work, nor do I believe that disability is best conceptualized as primarily the result of a lack of accommodation and of attitudes held by the non-disabled. Furthermore, I believe that these ideas are harmful to disabled people, not only because they induce a victimhood mindset, which is psychologically unhealthy, but also because they cause us to be hostile to technologies which really could improve our lives. For these reasons, I feel said ideas must be challenged. Going beyond science, therefore, future videos will also offer a philosophical defense for the perspective that our society should, in fact, be trying to cure disabilities. Elephant number two is the fact that all of this bleeds into transhumanism. For those who don't know, transhumanism is a philosophy that states that we ought to use technologies, such as those discussed here, to transcend traditional human limitations. This includes not only ending disability, but also enhancing the physical and mental abilities of everyone to superhuman levels. I do consider myself a bit of a transhumanist, although I need to do some more research before giving it my full endorsement. My interest primarily stems from a need for allies. I seem to presently be in the minority when it comes to disabled people and their attitudes toward cures, and transhumanism is a ready-made movement with goals that align with my own. Also, contrary to the usual objection that transhumanism might exacerbate inequalities, I suspect that its emphasis on enhancement might actually redound to the benefit of the disabled, since, as I pointed out in Part 4, a wider market base incentivizes innovation and drives down costs. Future videos will explore these ideas and other potential intersections between transhumanism and disability. I'm excited about what I have planned going forward, and I hope you are too. Stay tuned and take care. Thanks for watching the video. If you got something out of it, then please consider giving it a like and subscribing to the channel. You can also follow me on any of these social media platforms. And if you really like what I'm doing, you can support me on Patreon. The links are all in the description.